Next up, we have Visual Layer, and Visual Layer is building the next-gen AI tool for your computer vision data, and it is led by a group of visionary technologists, including Dr. Danny Bickson here, who has been working on AI ML with CMU and Apple since 2009. And he's here today to talk to us about the exciting features and innovations that he's working on to expand access to analysis for your computer vision data. Dr. Bickson, I'll let you take the stage.
Hello everyone. So thanks so much for the invitation, Eugene. It's super kind to invite us. And so I hope I'll try to share my screen. I hope it will work. Whoa, that's okay. Yeah, so I'll tell you today about Visual Layer. We are building tools to manage, visualize, and search videos on large-scale dataset, but you can start for free on your laptop and then go and scale to the cloud. So I'm Danny Bickson. Previously, I had a startup in Seattle. Startup was acquired by Apple, and I joined Apple Deep Learning Research R&D Center in Seattle, growing to 500 people. And I was working with my advisor, Professor Carlos Gestrin, from Stanford, who is now in Stanford. He was our CEO. Before that, I was working at Carnegie Mellon on GraphLab project, which was a popular graph analytics. And in a minute, you'll understand why it's relevant. We have a third co-founder, which is Dr. Amir Alush. She's a very seasoned computer vision researcher in Israel. So that's the joint work of the three of us that I present. And I do apologize. I just got back from CVPR in Seattle, so I lost a little bit my voice. So hopefully it should be fine. So the problem we are tackling is a problem of very large visual data sets that are accumulating, and companies have no clue what to do with them. Basically, they are left unattended, and this is because on a massive scales, when we talk to billions of images and videos, it's super complicated, not enough skill sets are around, and not enough tooling exists, so that's where Visual Layer comes in. We started with the open source approach called fastdup. That's our popular project. 2 days ago or 3 days ago, we got to 400,000 users, which is cool. And what we do the boring things of visual data curation, which means getting, it's kind of ETL for visual data. You get a lot of images and videos. You want to figure out what's inside. So first step, you always want to remove duplicates, outliers, corruptions, wrong labels, and wrong metadata. So that's what we do in fastdup. And under the hood, we have a C++ engine. I'll talk a little bit about what's the main concept behind its work, but it's really old-fashioned due to performance, and we can scale to up to 1 billion images or video frames on a single multi-core machine without any GPU. So that's a nice property of our tool. We have a lot of users. Some of them are paid customers, and a lot of also free users that use our open source. I want to share a little bit what are the typical kinds of issues we see on visual dataset, just to set the context. Why do we need our library? So the first thing, and this is all examples from ImageNet, it's a very popular dataset with 30,000 citations, and it's widely used in academia and also in research of companies. So the first annoying problem, we often got duplicates. So just duplicate images that don't contribute much to our knowledge, and we should just reduce them, and there is no additional information in them. Second type of issues that may happen with our images, sometimes images are too dark, and that's also may pose a problem to some model dealing with those side cases. If the model was not trained enough on dark images, the model may fail. Of course, the opposite, we often have also bright images, so that's often the case. And this is an example of blurry images that are also not too high quality, which we may want to filter those out, depends on the task. So besides of understanding the single characteristic types of data we got, we also have a notion of outliers. Outliers are images which are kind of different than the norm of the regular images. So I just pick from ImageNet images that we believe that they are outliers in some sense. Some of them are pretty weird, some of them I'm not sure exactly how to describe them, and some of them are just not common enough that are flagged as outliers. Now the next thing we'd like to understand when approaching a new data set is what's going on with the data distribution. So for here I picked a nice example. So of course dogs and cats are very popular item. Everyone takes photos of their dogs and cats. But here I'm asking interesting questions. How many instances of cats inside toilets we have in ImageNet? And surprisingly, there are a lot of such instances. And using our tooling, it's really easy to find them. I'll show in a second how. The next thing I said, okay, we have cats, so probably people like dogs. So I guess we also have potentially many dogs in our dataset, and indeed there are dogs in toilets, different types of positions in the dataset, which makes sense. But what if I would ask, are there any goats in the dataset inside toilets? So out of 1.3 million images, we were able to find a single goat that the image is taken inside the toilet. So this is a pretty rare event. So I would say the cats in toilets class is kind of, you could find hundreds of examples, but a goat inside a toilet, it's really a very, very corner case in terms of the outliers. This is another funny one that I found. I have no clue what it is, but it looks frightening. So I added it in the toilet category. So some weird people have this kind of toilets. And this is a bit of more artistic. People are doing some arts inside toilets, which is funny. And even they are drawing some pictures of toilets. So this is, again, another outliers. I wouldn't imagine someone named Sheila Hudson would bother a lot on taking photos of her toilet paper, but it's part of ImageNet. So that's a bit helps me to understand better my data set. Now, everything I showed is kind of properties of visual data sets. And what we're doing on top, we're building a platform which connects to all of those images I showed, and their metadata, their descriptions. We form a graph of relationship, and then we understand better what's inside the data, both for quality reasons, for ruling out corruptions, duplicates, and so on, but also for an analyst to be able to quickly find and filter interesting things on their data set. So this can run on-prem or in the cloud, and can run as an API or as an analyst user that is using the system, and I'll show you exactly how. So let me start with a quick local demo of our new latest and greatest Python package that we just released last week at CVPR. So I'll hop off the here, and I hope you can still hopefully see me. So what I have here, I have a Python console. What I'm doing, I'm calling Python, importing our package fastdup. The next thing I'm doing, I'm pointing to the location of bird images. That's a dataset that I have locally on my laptop. It's a popular Kaggle dataset of 90,000 images. And the next thing I do a run, which is basically drive the analytics out of this dataset. This one I will skip because I did it before the talk. It takes around 2 minutes for 90,000 images. And the next step, I would like to visualize. So what I do, not explore the dataset. So it opens a new window. So you can see we have this popular dataset. It runs on my laptop. It points to the local host, and I start to see interesting clustering. That's not part of the dataset. It's part of our visual clustering that we are doing the clustering and able to find similarity across different types of birds. And this relates to the graph engine we're building, which basically, starting from a single image, I can look at another image, and then start exploring around the other image, and then I can start continuing forever and understanding how my data looks like. So that's a powerful way of unsupervised exploration of the data using our graph technology. The next thing we also do automatic mislabel detection. So assuming there are labels, we can automatically point areas where we think there are mislabels, and mislabels are visual. So if a lot of this bird is most likely mislabeled as crested nuthatch, whatever it means, and the possible correction is titmouse. I don't know which bird it is, but that's more common in the data set in terms of the visuals. So we are pointing mislabels. One last interesting thing about this data set is the ability to flag outliers. So I'll go out of this context. And here we find a surprising find. So there are Trump images and all kinds of January 6th images hidden as an Easter egg in this data set. And of course, they are not birds. If we log into a specific image, we see this image is called loony birds. So someone had a political statement. I'm not American, so I don't really care. You should choose elect the one you believe in. But that's a bit of a funny because, as I mentioned, it's a popular Kaggle dataset with 65,000 downloads, and of course, no one has a clue what's inside. And as I show you, we can find in a few seconds what's unique about these datasets and what are the outliers there. So let me get back to the slides. And now I would like to do a demo that I also did in Seattle last week, which is a demo in the cloud, where in the cloud we have more advanced capabilities since we have more compute power in the cloud. So for the meetup last week, what I did, I just downloaded 70 TikTok videos, all with hashtag Seattle, and I did it very quickly, both because I'm lazy and also because I was at the Amsterdam airport. So I needed to do a quick demo. And this is the winning image, which is representative in Seattle. But actually, when I started to prepare this data set randomly out of 485 video frames, this dude showed up. So I guess this is less appropriate for a Seattle demo. So we switched the title. So let me show you how our system looks in the cloud. And now I'm switching, instead of the local host, I'm switching to the cloud. And this is our Seattle demo. So what I have here, relative to the previous data set, I have here video input sources, where I just give a folder of video files, and then we do all the magic in order to reduce and select the interesting video frames. We selected out of 75 videos, 485 video frames, and then we do enrichment in order to, and here it's our enrichment, in order to have a better understanding, sorry, what's in the video. So you can see number one popular cluster is skyscrapers. We have some nightclubs. We have, I don't know, food, Ferris wheel, toy shops, and so on. And one of the things that caught my eyes pretty quickly is this weird video. So I really have no clue what it is. But then I asked my fellow Seattle friends, and I found there is a gross gum wall in Seattle where people come and stick gums into the wall after eating them, or maybe vice versa. Maybe they take gums and eat them, I'm not sure. But anyway, that's a bit gross. So as you can see, when I enter a specific video frame, we also have an understanding of the actual objects in the video frame. And we have, in this case, multiple objects that I can start exploring, and that's done part of our enrichment. So if I want to do it more methodically, I can jump to the object scenes, and then here I see all the objects from all the video frames, from all the TikTok videos in Seattle. And then I have, for example, a car, is an object inside the video frame, and then I can press a button and start exploring the space of cars. So again, I'm traversing the graph, but in this case, I'm not traversing the direct video frame, I'm traversing something which is more complicated, which are objects inside video frames, but still same look and feel. And given a specific instance, I can start exploring, and assuming, let's say, I like this manga, I can start it as a query, and then start looking for other mangas and so on. So that's the way I traverse. Another thing which is cool in the cloud is the ability to do textual search. So I could do search a car, and then I get different types of cars. But if I'm very pedantic, I may want to bring in a red car. So I have here 2 red cars. Let's see what happened here. Oh, you see, there is a red car. Strangely, 3 was marked, but we have a red car, so we are good. So that's the ability to do complex textual queries, visual queries, and also exploring the graph structure, and also different types of slicing and dicing. So I could look at the label space and understand my data better. So I can look for blanket, and strangely, this is labeled as blanket. Yeah, so that's the cloud demo. Let me come back to my slides. So I wanted to take a few last minutes in doing a little bit of explanation of what's inside behind our system. So our foundation is built on the work we did on Carnegie Mellon about GraphLab. That was a pretty successful paper. Recently, we won a Test of Time Award with VLDB, which is nice. I mean, it was too late for my academic career, which ended prematurely, going to a startup, but still, it's a nice recognition. And what we did in this work is the ability to explore and interact with billion nodes, graph, and edges already in 2009. So those was my collaborators here. And if we link it back into the visual domain, so basically this is a very, very naive representation showing our famous cats and toilets clusters. So what we have here, we have input images. What we do feature vector embedding of the input image into a short feature vector. Then we build a nearest neighbor model in order to understand relations between distances between images, and images that are has a close distance, which means they have a high similarity, which means they are more or less clustered around certain small regions of the graph. And once we have an object which is common in both those images, our expectation would be that the cats with toilets cluster would be somewhere in the middle between the toilet cluster and the cat cluster, and then we can do some kind of interactive exploration, which gives us very cool results and a much better understanding of our data sets. Yeah, so that's what I wanted to share. Thanks for listening or viewing. And anyone who likes to check it out, would love to have you install. Just pip install fastdup. As I said, it's a free package, and this is my email. And anyone who wants to outreach, I would love to connect and explore to see if we can help with anything. And I would love to take questions in case there are any questions.
Okay, so this was, we're about 12 minutes off from our next scheduled talk. But we'll see if there's any questions in the audience. I have a question for you while the audience kind of like puts together whether or not they have any questions. Could you talk a little bit about like the complexity of the pipeline that goes into taking the data from the raw data format into putting it into something that is able to be accessed and analyzed as you show in fastdup?
Yeah, sure. So that's a good question. So what we do, we typically Our API is super simple, so we assume you have a folder or a bucket with a mix of video and images. That's all we need. If you have metadata like image annotation, that's fine. We support also class labels and bounding boxes. So the first thing that we do once we connect to your bucket, and by the way, we can run on-prem, so it can run close to your data. It doesn't need to, data does not need to ship to us. And so once you connect, we connect to the bucket, what we do a scanning of the data. In case of video files, we do frame extraction. So we have our own way of doing efficient frame extraction. Again, this is done in C++, no GPU, so that's a very efficient step. And the next thing we do after the frame extraction, we do a deduplication step between the frames and the images. So you may have some screenshots of videos, you may have duplicate videos, you may have overlapping videos and so on. And so, sorry, that's we do to reduce the amount of redundancy in your data. The next thing we do also what we call an enrichment, which is the object level and the description understanding of the frames. And that allows us to do also textual queries, which could be combined of a few terms, like description, like a man with a red hat driving a white car, for example. That could be a query. And once we've done the enrichment phase, then we do the clustering in order to group similar objects together. Maybe I can show it really briefly, and then it will be much more clear. Yeah, here it is. So this is, for example, a cool YouTube dataset that we're using, 15,000 videos from YouTube. And I hope you can see my screen. So what we have here different types. After we do the enrichment, we cluster different types of activities. And then what you could do, you can investigate the different types of activities and jump to the specific video where this activity happened. So that's the clustering, which is done after the enrichment step. The final thing, besides of the exploration and visualization, we allow also what we call an extraction. And so that allows you to find interesting things on your data and create downstream data sets. So for example, assume I really like soccer or football, and then I can select a few clusters containing football videos. And then what I can do, I have this type of shopping cart. Oh, sorry, I forgot to move. Let me re-add. Sorry. So I have selected a few clusters. And then I have this shopping cart. And here, what I could do, I can assign a new class, basically. So what I could do, I can press the plus sign, say this is a new soccer, create a new class. The tags were created. And next, I could go back to this annotation, look at the user tags into the new soccer class, and then I can pull up whatever information I wanted, and I can also extract it to create high-quality datasets for training. So that's basically the functionality. It's pretty efficient. Largest customer, our latest deployment has 100,000 hours of video. So I guess that positions us on the really large scale side of solutions.
Cool. Thanks for that. One other, I guess, Megan, did you want to ask any questions?
Oh, no. Go ahead, Nugent.
Okay. One other question I wanted to ask before we move on is also, like, how do you handle this kind of scaling? Like, what are you doing in the background that makes it possible to scale to these hundreds of thousands of hours of video? Is there any what is the secret sauce behind this? Are you able to tell us what this is?
Yeah, it's an interesting one. So under the hood, we deliberately devised the code in C++. It's a lost art for the elder, I would say. and it also gives us some advantage that we can provide a compiled binary. So it's very small binary. It works very smoothly in Python, but we don't disclose everything in front, basically, because we do have want to be a company that eventually charges for something. Although the open source is free, also the cloud version you can sign up for free. So what happens? We do very efficient feature vector extraction. After the video extraction, it's also done in C side. We do a very efficient feature vector extraction. We devise the network that's very lightweight. It's just 2 milliseconds per core. So it doesn't make sense to use GPU because you don't want to copy the images to the GPU and back. It will take more than 2 milliseconds. So that's very efficient. Feature vector representation is pretty short. We can keep it in memory, and that's how we can scale on a relatively beefy machine, but we can scale to 1 billion images on a single machine. And they're just one machine. So we built the nearest neighbor model. We have our own implementation of the graph on the C side. And that's our claim to fame. So we are graph people. So basically the trick is to, instead of working with 1 million pixels per image, we boil down the image into a single graph node, basically. So that becomes very efficient in terms of representation. We don't work with the raw image to show you the cool analytics. We do traverse the graph. It's very condensed representation, so the graph is pretty small. And once we want to scale into more, we can start opening shrouds in order to have subsets of the data. So let's say for, I would say 100,000 hours of video, probably it will be some like 10 shards that will contain 10,000 hours of video. And then so it's a bit of a hierarchy there, and then you can explore them one by one.
Okay, and you guys are using your own embedding models? You guys have your own embedding models?
Yeah, we developed our own embedding model. Anyone trying to reverse engineer will see it's called undisclosed fastdup model. There are a few, let's say, GAMP companies that try to reverse engineer, but deliberately we didn't want to share it. So basically, you can use it for free. So if you just want to do embedding, fastdup supports that, and you do it for free. But we don't give the right network architecture. It's just very lightweight network architecture, but we also support others. So if you have a better network for your own needs, we support out-of-the-box EfficientNet, ResNet, Dino, V2, and many others. But if you have yours, it's pluggable. So we did observe some customers that had very specific needs. So for example, customer growing mosquitoes had mosquitoes with white dot on the tail. And then they would kind of complain, how didn't you find the white dot on the tail? And our embedding model was not designed for such minute detail. But they have their own embedding, which is really, really distinctive across sub-mosquito types. And it's always like that. Like for each type of data set, you have different type of requirements. So we have something that generally works really well for a variety of data sets, but it may be that your embedding could be better for some cases.
Okay, cool. That's really interesting. I don't know if there's any other questions from the audience. I don't see any this time. I think we can move on to our next talk.
Very good. Thanks for the invitation.
Thank you, Danny.
Have a nice day. Bye-bye.
See ya. Thanks for coming.